All right, so let's go ahead and take a look at an example problem. I want to make sure that we are comfortable solving calculations involving conservation of energy and writing energy transfer equations to show energy changing from one form to another. So that's what these problems are going to let us practice. The first one says a 15 kilogram mass is moving at 7.5 meters per second on a horizontal frictionless surface. What is the total work that must be done on the mass to increase its speed to 11.5 meters per second? So in this problem, we have an object that is currently moving, and we want to make it move faster. If you read the question, it wants to increase its speed. Okay, so we need to identify the form of energy present. So with it initially moving, we're starting out with an initial amount of kinetic energy. And at the end, if we read through the scenario, we still have it moving. It's still moving, but now it's moving faster. So we're going from an initial kinetic energy to a final kinetic energy. However, there's also work being done. We have a change in our total mechanical energy if we have a change in our velocity here for that same object. Then we have to have energy added into the system. That's the only way to get it to speed up. We need an external force, and we need work being done. So we have to have some amount of work done in order to increase that velocity so that we have more kinetic energy at the end than we had at the beginning. I'm waiting for this to focus. Okay, so you have to first be able to write an energy transfer equation. Ours is going to look like this. We're going to go from having initial kinetic energy based on our initial velocity of 7.5 meters per second to having a final kinetic energy that is greater because the velocity is greater at 11.5 meters per second. And again, in order to increase the total energy of our system, we have to have work done by an external force. So if we want to solve this problem, we need to go ahead and break this down into variables. Because it doesn't give us the KE, it instead gives us things like mass and velocity. The equation for kinetic energy is 1/2 mv squared, so we're going to plug in our initial values over here. Work, you could plug in force times distance, but it actually doesn't ask for force, it just asks for the total work, so I'm going to leave the W in here. And for final energy, we're going to have 1/2 mv squared. Substituting in, half the mass here is 15. The initial velocity is 7.5. This is going to be squared per that equation. Plus the work that is done will equal 1/2. Again, mass is still 15, doesn't change. And the velocity at the end is 11.5 meters per second. And again, we have to square that. So that is your substitution step. We did the physics. From here, it's just algebra. So if we want to solve this, we're going to go ahead and pull out our calculator. And we can type in what we have here. So half of 15 times 7.5 squared. This represents our initial kinetic energy of 421.875 joules. And again, we're going to add some work to that to get us a final KE. And again, we're going to multiply the same way, except this time we're going to use 11.5. And it'll give us a final kinetic energy of 991.875 joules. Again, we're not going to round until the end, but you can see here that clearly we have increased the energy in our system, and again, we did that because work was added. How much work? Well, you can look at these values here. We went from having about 420 to about 990, and if we want to figure out exactly how much work that was, we can do so by subtraction. I can take this answer that we just had and subtract from it that one right there to get the difference. That's going to be how you determine the amount of work done. The work in this case is equal to 570 joules. So by doing 570 joules of work, by pushing or pulling this box to get it to speed up, we're able to get it to increase its energy to 991.875 joules at the end. But this is your work. Okay, so again, in order to solve these, you have to be able to write those energy equations. Let's go ahead and take a look at another example and see if we can do this one in much the same way. Okay. Get a fresh sheet of paper here. And it says, The diagram below shows a toy car possessing 16 joules of kinetic energy traveling on a frictionless horizontal surface toward a horizontal spring. If the cart comes to rest after compressing the spring a distance of 1 meter, what is the spring constant of the spring? Again, in order to solve this problem, we first have to identify the energy that is present initially and the energy present at the end and write ourselves an energy transfer equation. Initially, this car is moving. It says it up in the question. You can also see it in the picture. It has KE. And so the initial energy that we have in this scenario, this example, is kinetic energy. That kinetic energy is going to be transferred to the spring because it says that it comes to a rest, meaning it's no longer moving, and that it compresses the spring. Well, whenever we have anything being compressed or stretched, we are dealing with elastic potential energy. And so we can simply set our equation up as the initial kinetic energy, the initial motion of the cart, is going to entirely be transferred to the spring in the form of elastic potential energy. From here, we can go ahead and break these down into variables where we need to. We don't need to break this one down because it actually tells us that there are 16 joules of kinetic energy in the question and in the picture. So we already know that this is 16 joules. We just need to figure out what the elastic potential energy is. And so we do want to go ahead and plug in the equation for EPE, which is 1/2 kx squared. In this equation, k is your spring constant, and x is the amount of deformation or displacement of your spring. In this problem, we're actually solving for the spring constant, so we're going to be looking for k, and we actually know the x, the displacement of the spring. So if we go ahead and plug in the rest of these values, we have 16 equals 1/2 k times the amount of displacement of the spring is 1 meter, 1 squared. And if we solve from here, 1 squared is 1. Half of 1 is a half. And so we end up with 16 equals 1/2 or 0.5 times k. If we want to solve for k to isolate our variable, we just need to divide both sides by 0.5. Dividing by 0.5 is the same thing as multiplying by 2 because we're dividing by a half right now, which means that if we do that, we're going to find that we have a K of 32 newtons per meter. All right, let's look at another problem related to this one, just as an extension piece. In this problem, it said to assume that it was frictionless, but let's pretend for a second that it's not. What if we did this exact same experiment, but on a surface that had friction? And that's what the second part of this question says. If the same experiment was repeated on a different surface with a frictional force of 2 newtons, so let's go ahead and label that. Exerted on the cart over 5 meters, there's a distance. How much would the same spring be compressed? So if we're dealing with the same spring, we're dealing with the same spring constant. All right, so if we want to solve this, okay, similar problem, but we do have to re-examine this equation because if we include friction, that means we have an open system, and that means that our initial energy and our final energy aren't going to be the same because mechanical energy is not conserved when we have frictional force. That's an external force acting on our system. So let's go ahead and rewrite the equation first. We still have kinetic energy initially, but now that kinetic energy that was all transferring to EPE, well, now some of it's not. Some of it now is going to be lost due to heat dissipated from our system due to friction. And so we still have the elastic potential energy, but we're not going to have as much because some of the energy that started out as kinetic is now getting wasted as heat along the surface. So we don't get to squish the spring as much as what should happen whenever we solve for this. I do want to make a note that thermal energy here, due to friction, you could also call it work due to friction. Friction does do work because it applies a force for a certain amount of distance. That's actually what we're going to be using, but we usually write it this way in my class. But again, it is work because it is a force applied for a certain amount of distance. It just so happens that friction, whenever that work is done, produces thermal energy. And I'll address that at the end, the difference between the thermal energy and the work with regards to how you report your answer. But work is change in energy, and this is going to represent change in energy that occurred between these two. Okay, so let's go ahead and solve this one. Our variables for KE it didn't have a variable, it was just 16 joules. That's still there because we're doing the exact same scenario. The EPE, this time we know that we have the same spring, so we have the same K. So we're going to have 1/2, I'll just go ahead and write the variables now, 1/2 kx squared plus, and again for thermal energy over here, they actually gave us the force and the distance that the friction is acting over, which means we actually do have to solve for work here. So we're going to have plus that force times distance in order to get the work done by friction and include that over here. Okay, so from here, if we want to go ahead and substitute in, we have 16 equals 1/2. The K in this case is the same because it said to use the same spring, so 32. We're going to be solving for x, and then the force of friction is 2 newtons, and the distance that friction acts over is 5 meters. So this would be your substitution step. So we have 16 equals 16x squared plus 10. Okay, so from here, if we want to solve for x, we do need to isolate our variable. You cannot add these. Some of you keep trying to add things like that together. You cannot do that. Okay, those are not like terms. So to get this by itself, we are going to eventually have to move this 16, but the first thing we're going to do is move this 10 by subtraction. Subtracting 10 from both sides, that gives us 6 equals 16x squared. And then from here, to isolate our variable, our next step is going to be to move that 16. In this case, we're going to divide. And so in our calculator, 6 divided by 16 gives us 0.375 equals x squared. Again, that's not our final answer because we need the square root of that. And that gives us x, the amount of compression, as 0.61 meters. Again, guys, make sure your answer makes sense. We just said at the beginning, before we did this, that we were going to lose some energy along the way due to friction. Okay, and so our spring shouldn't be compressed as much. If we look back at the first question, the compression of that spring was 1 meter. It's less now. That makes sense. It should be less. Okay, so just make sure that your answer makes sense. But that is how you handle friction whenever it's added in. Just as a side note, sometimes it'll say thermal energy dissipated due to friction, or energy dissipated due to friction, or energy lost due to friction, and all of those things are going to refer to energy. But again, friction does do work because it is a force and it does act over a distance, and so you can also use the W there. And we'll look at it again with the next problem. This will be the last one in this video. Let me get a fresh sheet of paper. And it says, a 2-kilogram block slides from rest down a ramp from a height of 3 meters above the ground. I'm going to go ahead and draw a picture. Of our block sliding down this ramp. Okay, so we have a 2-kilogram block sliding from rest down a ramp from a height of 3 meters above the ground, and when it reaches the ground, it has a kinetic energy. So down here, once the box is here, the KE is going to be equal to 50 joules. Maybe it's sliding along the ground. It doesn't say. It doesn't matter. We just need to know that. The total work done by friction on the block as it slides down the ramp is approximately. So this was actually asking us for work done by friction. All right, so let's go ahead and write our energy transfer equation. Before we can solve this, again, we have to know what we're solving for. So initially, when it's at the top of the ramp, that block has gravitational potential energy. That gravitational potential energy is the only thing up here because it does say from rest. And of course, there's nothing happening here that would imply that we have any amount of EPE. So it's just GPE due to the height. And that GPE, as it goes down, is going to turn into KE. But this is not your entire equation because the question also implies that there's friction. It wants to know the work done by friction. Doesn't mean there has to be friction. It could turn out that there is none, but we do want to include it here. Again, if there's friction, I'm writing TE. It does say in the question work done by friction, but again, if this is the way that we're typically designating friction, and so this is how I'm going to write it, it would be just as acceptable for you to label it as work, and you're welcome to write a W if you want. But from here, let's go ahead and solve. So it doesn't tell us the GPE, but we can find it because GPE is mgh. It does tell us the KE. It says that at the bottom of the ramp it has a kinetic energy of 50 joules. And again, this is what we're looking for. We're looking for the work done by friction. But again, work is change in energy, so I can solve for the energy and get the work from it that way. Let's go ahead and substitute into our equation up here. The mass is 2. Since it says approximately, we're going to use the approximate value for G, which is 10, and the height from the top of the ramp is 3. That is equal to 50 plus the thermal energy. Again, if these are equal, we can say that there was no thermal energy, there was no friction. If it turns out that the GPE is 50 and the KE is 50, it's frictionless. But if it turns out that we had more energy and we don't have as much at the end, then we know that some of it was lost along the way and it was dissipated out of the system, most likely as thermal energy due to the friction of the surface. So let's go ahead and multiply over here. This is a 3. 2 times 10 is 20, times 3 gives us 60 equals 50. That's your GPE initially, that's your KE final. Those are not the same, which means there was friction. We lost some of our energy along the way. How much did we lose? Again, you can see it right there. This one's easy. We lost 10 joules, but again, you're solving for TE. To do that, you subtract 50 from both sides, and you find that the thermal energy produced, the amount of energy produced due to this friction is 10 joules. That's the amount leaving our system. Now, the question doesn't actually ask for thermal energy. It doesn't ask for the energy dissipated from the system or the energy lost. The wording of the question is what is the total work. So let's address that because we got to do one more thing to this answer. Energy is scalar. It doesn't denote a direction. There's not a sign. It just is a number value. It's not positive or negative. But work can be positive or negative because work is a change in our energy, and work can be done to add energy into our system, like if we push something in that previous problem that we did that. Or it can leave our system if the force is acting against the motion of our object, which is exactly what friction does. Friction takes energy out of the system. In this case, we lost 10 joules. So when we write it as energy, it's going to just say 10 joules. But if we wanted to denote it as the amount of work done, we need to include a sign. In this case, our system lost 10 joules of energy, and therefore the work done is negative 10. If it had been energy added in, something pushing it, then that would have been a positive number. But in this case, friction is always going to be negative because it's always going to work against the direction of motion of your object, so it's always going to be slowing stuff down. But this is the answer that you would want to report based on the wording. If it had asked just for the energy dissipated, you could have left it like that. But if it asks for work, do pay attention to the sign. Again, in order to solve all of these problems, though, the first step is always to write your energy transfer equation.